Okay, the next speaker is Daniel Grier. He'll tell us about the complexity of bipartite Gaussian boson sampling.
Okay, yeah. So yeah, thanks everyone for coming. This talk will be about the complexity of Gaussian boson sampling. It's joint work with Daniel Broad, Juan Miguel Arrazola, Benicio, and Nicolás Quesada. And if you're not sure what this word bipartite means, that's actually good because we made it up. But hopefully it may be a little bit clearer later, but maybe not too much. I wanted to sort of start by asking sort of what is by now sort of like a relatively well-established question in the field, which is, is it hard to classically sample from the distributions produced by weak photonic quantum computers? And by now we have several strong candidates for specific linear optical experiments that you could run that would lead to this kind of quantum computational advantage. Perhaps the most famous is boson sampling, or as I will sometimes refer to it in the stock, Fock boson sampling, introduced by Aronson and Arkhipov over a decade ago now. But there are a growing number of other proposals. So we just saw in the previous talk the fermionic sampling with magic input states. And more recently, Gaussian boson sampling has come to the fore, due to some sort of impressive sort of experimental realizations of that specific proposal. But unfortunately, sort of despite sort of the diversity of these proposals, there's some reasons to be unsatisfied with the current state of the theory. First, because each proposal involves linear optical systems with slightly different dynamics, the hardness of classical simulation arguments are based on slightly different conjectures. And so some of you may be thinking about scattershot boson sampling, which is an example of something that actually does help to sort of close this divide. It connects the hardness of Gaussian boson sampling with the hardness of Fock boson sampling. But unfortunately, sort of both with this protocol and others, we will see that sort of extra conjectures are required to make the theoretical hardness arguments there align with the realities of some corresponding experimental realizations. So I'm going to talk a lot more about exactly what I mean by this later. But first, let me sort of just introduce our technique for addressing these issues. There's a specific method for programming a Gaussian boson sampling device, which we call bipartite Gaussian boson sampling, or BipartiteGBS. So let me lay out a few of the advantages of this approach. So first, like we saw with scattershot boson sampling, we're able to base the classical hardness of this Gaussian boson sampling experiment on standard conjectures that were used for Fock boson sampling. However, unlike scattershot boson sampling, BipartiteGBS will actually allow us to circumvent the need for a conjecture that was required for Fock boson sampling. Namely, we'll be able to show rigorous hardness in the regime where the number of modes is quadratic in the number of photons. So this is a setting which was widely believed to be true. In fact, people sort of talked about it as if it were true. But to the best of our knowledge, it had no definitive proof. And so much of the rest of this talk will focus on exactly sort of where this conjecture comes up and how we circumvent it with this construction. But finally, I want to mention sort of another nice part about this BipartiteGBS construction, which is that sort of quite general and versatile. And so we hope that it will become sort of a useful basis on which to build other classical hardness arguments. So for example, using BipartiteGBS, we can show hardness in a regime with constantly many photon collisions. And we provide an outline for how one might obtain classical hardness in the high collision regime, which I'll talk a little bit more about later as well. So, since we will ultimately be sort of reducing the hardness of BipartiteGBS to the standard conjecture required to show that Fock boson sampling is hard, let me spend some time revisiting that result. So the original theorem of Aronson and Arkhipov states that it's hard to approximately sample from the distribution of outcomes that result from scrambling single photon input states by random linear interferometers. So sort of the picture that you should have in your mind is the following. So we have input states that consist of n indistinguishable photons that are located in m distinct modes. And the linear interferometer is described by a unitary that acts on the modes of this state. And in a boson sampling experiment, we simply shoot these photons into the interferometer, then measure and see where they end up. And sometimes we'll describe these states in this ket notation here simply as sort of the list of the photon counts in each mode. And specifically, these output probabilities are given by the function of the submatrices of the unitary matrix, which is describing the system. So for example, on the slide, I've shown a unitary for a 5-mode linear interferometer. And sort of to calculate the probability of obtaining a measurement outcome, say with photons in the 2nd and 4th and 5th modes, from an initial state where we have 1 photon each in the first 3 modes, we look at the corresponding rows and columns of those elements, and then we compute the permanent of that submatrix. And if there's more than 1 photon in a particular mode, then we just take that corresponding row or column multiple times into the submatrix. So now in more detail, the main theorem of Aronson and Arkhipov is the following. So there's no classical polynomial time algorithm to approximately sample from the output distribution of a boson sampling experiment, modulo 4 conjectures in complexity theory and random matrix theory. And I will touch upon some of these other conjectures later in the talk, but for now, I only want to focus on this last conjecture. And in fact, sort of glossing over the precise statement of this conjecture, let me now sort of claim without proof that it has the following physical interpretation, which is that we get hardness in the regime where there are quadratically more modes than photons, or in other words, where m is roughly n squared. But what if sort of in an attempt to make our hardness argument more rigorous, we tried to make the same argument, but without this last conjecture? So Aronson and Arkhipov then show that they can get classical hardness in the regime where m is roughly n to the 5th power. And in fact, this relationship between the number of modes and the number of photons must also hold for traditional Gaussian boson sampling proposals. But unfortunately, when we look at real-world Gaussian boson sampling experiments, we see that this parameter regime where the number of modes is much, much larger than the number of photons, this does not really match the reality of what's happening in the lab. In the first of 2 sort of high-profile experiments coming out of the USTC group in China are about 45 photons at 100 modes, and the second of these experiments are about 113 photons at 144 modes. So you can see that incorporating many modes into the experiment is costly, which is why we see that the number of modes in each experiment is not much more than the number of photons. So the theorem that I want to show you is that there is a Gaussian boson sampling experiment in this regime where the number of modes is quadratic in the number of photons, that nevertheless only requires 3 of the 4 standard conjectures from boson sampling. So I'll first describe sort of exactly where this conjecture is being invoked in the hardness argument of Aronson and Arkhipov, and then I'll sort of describe this general construction called BipartiteGBS and sort of how it allows us to dodge this problem. So let's return to our picture of the dynamics of a Fock boson sampling experiment again. And it will turn out that the hardness of the boson sampling protocol is based on the hardness of computing permanence with ID Gaussian entries. So in particular, this property implies that these n by n submatrices that appear in the outcome probabilities must themselves look like matrices with ID standard complex Gaussians. So that is, whenever this random unitary n by n random unitary matrix U is chosen from the Haar measure, then its n by n submatrices look Gaussian. But this is sort of exactly the requirement that is causing a problem. We only have rigorous convergent bounds Gaussian whenever m grows faster than n to the 5. And for those of you who know some of the results in this area, this may be a bit surprising to you. So I thought I'd spend a little bit of time sort of addressing the previous work on submatrices of Haar random unitaries. So the closest result that we are aware of is a result of Zhang, who showed that the distribution of n by n submatrices of random m by m real orthogonal matrices converges in total variation to the distribution of matrices with ID Gaussian entries whenever m grows faster than n squared. So this seems like this is basically giving you the result that you want. Unfortunately, there are sort of 2 issues with this result and using it in the boson sampling hardness arguments. The first is sort of a minor issue, which is that the theorem is about real matrices rather than complex ones. Though you could sort of easily envision sort of a real version of the original boson sampling proposal that's based on real matrices rather than complex ones, and you would just circumvent this problem by definition. But a second issue, which is a bit more insidious, is that this theorem does not bound the rate of the convergence to Gaussian. So in order to bound this rate, Aronson and Arkhipov actually had to assume that m was larger than n to the 5. And so our goal was not to try to improve this theorem of Aronson and Arkhov directly, but rather to sort of subvert it. So instead, we give a sort of specific construction of a device that allows us to circumvent the need to talk about submatrices of unitaries. And in particular, this BipartiteGBS construction, the output probabilities are going to be governed by permanents of arbitrary matrices rather than unitary ones. So let me sort of sketch what this setup looks like, and then we'll get into the details. So we start with two M-mode linear optical interferometers, U and V. And the input will consist of pairs of entangled Gaussian states called squeeze states. And each pair will have its own squeezing parameter. And similar to sort of Gaussian boson or normal boson sampling, we sort of shoot these squeeze states into the interferometers and measure. And we find that there will be an equal number of photons in both the left and the right outcome. And what you can show is that with a careful choice of your two unitaries U and V and the squeezing parameters, the output probabilities will be proportional to the permanent of a submatrix of an arbitrarily chosen matrix C. So these probabilities will be calculated in sort of the usual way. So for our specific left and right outcomes here, we compute the probability by sort of looking at the permanent of the corresponding submatrix. And because we wanted to base our hardness argument on the permanence of Gaussian matrices, somewhat sort of obvious in retrospect idea is just to simply start with a matrix that has IID Gaussian entries. So in particular, there's no reason to worry about the convergence to Gaussian. Like the matrix is IID Gaussian by design. So what are these input states and probabilities? So let's take a closer look at what's going on here. So the input states are written down as two-mode squeeze states, and they have sort of the following description when written out in the photon number basis. That is, the input states are superpositions over two-mode states where there are an equal number of photons in each mode. And sort of something to notice here is like there's no sense in which these input states contain a fixed number of photons. So to talk about the number of photons in a Gaussian boson sampling experiment, we actually talk about sort of the expected number of photons that you would measure if you measured in the photon number basis. But now suppose that we want to calculate the probability of measuring, say, the left modes in the state S and the right modes in the state T. Then this probability is given by the permanent of this matrix C in the usual way, where this matrix C is sort of most easily understood as the singular value decomposition of a matrix. The singular values are given by the squeezing parameters, and whose left and right unitaries are given by the left and right linear interferometers. Or in other words, if you could control these various parameters, you could set C to be arbitrary. And this setting may be, once again, familiar to many of you. So if you set V equal to the identity and the squeezing parameters to be constant, then you recover the original scattershot boson sampling protocol. So this is somehow just a generalization of scattershot boson sampling. So given this construction, let me now try to sketch sort of the entire hardness argument. And sort of it may seem very familiar to you because by design, it's going to mirror the same general steps of the original Fock boson sampling hardness argument. So first, we start by supposing that there's some classical algorithm that can approximately sample from the output distribution of any bipartite GBS experiment. That is, the statistical distance from the true bipartite GBS distribution and the distribution that the classical algorithm samples from are close. So we will leverage this classical algorithm to solve a problem known as Gaussian permanent estimation. So it's defined as follows. You're given an n by n matrix X with IID standard complex Gaussian entries, and your goal is to estimate the magnitude of the permanent of X squared to epsilon times n factorial additive accuracy with probability at least 1 minus delta. And this problem is conjectured to be sharp p hard by Aronson and Arkhipov, and in fact, we will need this conjecture as well. So how do you use this classical sampling algorithm to estimate the permanent of X? That's really what we're trying to do. So first, we want to calculate the permanent of X. So we hide this matrix X in some larger m by m Gaussian matrix C. This is quite easy because since C is itself a matrix with IID Gaussian entries, we can just choose some random submatrix of it to be X. And by the BipartiteGBS construction, we can configure the experiment such that there is a transition matrix that has some output probability that is proportional to the permanent of X. And using Stockmeyer counting arguments, we can then estimate what this probability is, and therefore estimate the permanent of x itself. And so finally, by the conjecture, this will imply the collapse of the polynomial hierarchy, because we will have estimated permanent of x using the Stockmeyer counting argument. And since the polynomial hierarchy is itself conjectured to be infinite, this is a contradiction. So you must not have had a fast classical algorithm to sample from this distribution. And so the tricky part here, which is sort of different from the normal Fock boson sampling here, is step 4. So what's going on here? So recall that we're trying to solve this Gaussian permanent estimation problem, which requires us to estimate the magnitude squared of the permanent to epsilon times n factorial additive accuracy. And what we can show using the Stockmeyer counting argument is that there's some algorithm which gives an additive epsilon times this normalization factor z times some exponential factors in n and m. And so you look at this thing, we need this to be epsilon times n factorial. So is this estimate actually any good? In particular, this estimate depends on this normalization factor z, and z depends on the singular values of a ID Gaussian matrix. So we're kind of faced with this sort of unpleasant sort of possibility here that after all this work, we've just sort of traded one problem in random matrix theory for another. We no longer need to worry about submatrices of unitary matrices, but now we need to sort of provide tight bounds of some function that depends on the singular values of a random Gaussian matrix. But sort of happily, this is not the case. So we can show that at least in the m equals n squared regime, this random matrix theory problem is one that we can actually solve. After some algebra shows that the estimate and lemma is actually good enough to solve this Gaussian permanent estimation problem. And I'm not going to really go into the techniques at all, but sort of the main tool is that if you look at the inverse of this normalization factor, it is the characteristic polynomial of what is known as a Weishart matrix. And so a lot is known about these types of matrices from random matrix theory. And so using some of these things and the fact that the singular values are small, we can prove this theorem. So let me just wrap up by sort of describing where we hope this research might go. So we showed the following theorem. So it's hard to approximately sample from the output distribution of a Gaussian boson sampling experiment in the m equals n squared regime under the standard boson sampling conjectures. So another way to look at this result is that we proved hardness in the no collision regime. Whenever the number of modes is quadratically greater than the number of photons, you're sort of extremely unlikely to measure 2 photons that end up in the same mode. But a sort of natural and important question is whether or not we can obtain hardness in the high collision regime when m is much smaller than n squared. And as we saw earlier, these outcome probabilities will now be given by permanents of matrices with repeated rows and columns. And so, in fact, it will turn out that through our bipartite GBS construction and sort of actually, unfortunately, sort of an additional random number theory conjecture, we can show that a classical sampler in this regime allows you to solve what we call the repeated Gaussian permanent estimation problem. So I'm not going to sort of read this out, but there it is. But if you were to conjecture that this problem is sharply hard for typical collision patterns, then you'd be able to conclude that classical sampling is hard in the high collision regime as well. But I sort of want to stress with many caveats that this is quite speculative and untested at the moment. So more work is needed to really figure out what's going on here. So I'll stop there. Thanks.
Right, great. Let's start with some questions.
Hey, Daniel, thanks for the great talk. Do you know anything about how experimentally feasible your setup is versus the usual one? I mean, the obvious question. It looked almost the same, except you put these like squeeze states across the 2 copies, right?
Yeah, it should be, I mean, I'm not experimental. I think it should be pretty simple. I think the downside is that, like, in some sense, you're using some of the degrees of freedom in the system to do the construction. So like in reality, because we have so limited resources, you probably just want to use all of those that you can. But my understanding is that it's not that hard.
So this repeated Gaussian permanent estimation problem, do you know when it's obviously false?
Well, it's obviously false when like all of the collisions are
is
like,
there a non-trivial regime?
No, we don't know when it's obviously false. We actually have some So some reason to believe that it's true is like all of the, all of the sort of complexity is sort of stuffed in the statement where it's for typical collision patterns, right? You really have to focus on the collision patterns that are typical for this Gaussian boson sampling machine. And we can show with some sort of numerics and some analytical calculations that the number of clicks in your distribution is large. And so if the number of clicks is large and you have high rank matrix permanence should be hard to compute. And so that's some intuition, but getting the exact error bound is, that's definitely more speculative.
Great. Any further questions? Okay, if there's nothing else, let's thank the speaker again.